So, thank you very much. I'm very pleased to be here, and I'm very pleased to have this opportunity to give a series of lectures about new results concerning the classification of class 7 surfaces, and especially the role of gauge theory, of Donaldson theory in this area of mathematics. So I want to thank very much the organizers for all the conditions they assured here for everybody. And I will start my talk with an introduction. So, about the contents of this series of 4 lectures. So, what are the goals? What I'm expecting to prove? So, what will be the final results? The ideas, and second, I will start with the gauge theoretical part of the theory. So this will be about Donaldson theory in general. So this will be an introduction about the role of Donaldson theory, first of all, in differential topology, where it appeared, for which it has been developed. So Donaldson theory in general as tool in differential topology. So at this moment, there will be absolutely not evident, not obvious at all, why this theory and in which way this theory will be relevant for our purposes, for our goals. This will be just history of mathematics, Donaldson theory from a differential topological point of view. And then, today also, I will speak about the complex geometric interpretation of Donaldson theory, which is mathematically is given by the so-called Kobayashi-Hitchin correspondence, which is a correspondence relating gauge theoretical objects to complex geometric objects. And in this way, so only at this moment will be obvious for everybody that Donaldson theory has connections with complex geometry. So this will be the goal for today. So, first of all, about introduction. About the introduction. What is the goal? The goal is to make progress, to announce progress, and to explain you the methods, the new methods, concerning the classification of class 7 surfaces. What are class 7 surfaces? So, main goal, classification of class 7 surfaces. So it's about the old Enriquez-Cordaira classification problem for complex surfaces. By complex surface, we always mean a smooth, compact, two-dimensional, complex manifold. So connected, connected, compact, two-dimensional, complex manifold, without absolutely no condition, no Kählerianity, no projectivity. So in the most general sense, as, for instance, introduced in the book of Bart Hoolek, Peters, van der Ven. You see, very often the classification of surfaces is treated or is explained from an algebraic geometric point of view. And then very often people have the impression that the problem is solved. Problem is solved. In dimension 2, the algebraic geometers say the classification problem is in principle solved. What only it remains to explain is to the moduli spaces for surfaces of general type. So this is the point of view of the algebraic geometers. However, if we allow non-algebraic and even non-Kählerian surfaces in our class we want to classify, the problem is completely different. We have here a very difficult to understand class, the class 7, which is defined in the following way. So is X complex surface in the sense I explained, complex surface, with the following invariants. B1 of X is 1, and Kodaira dimension is minus infinity. So you see the first condition shows that we are in the non-Kählerian framework. Such a complex surface cannot be Kählerian because the first Betti number is odd. So not classified yet. Not classified yet. Here, several things should be mentioned from a historical point of view. We have here the first example of compact manifold which is not Kählerian. This is the famous example of Hopf, which is a surface in this class. So the example of Hopf is a surface in this class. And this is defined in the following way. The first Hopf surface, at least, is the punctured plane factorized by a very simple transformation defined in the following way. Let's say u v is alpha u beta v, where traditionally one chooses here this period, these weights, in such a way that T is a contraction. T is a contraction on the plane, linear contraction. And one can prove easily that it is smoothly equivalent, differentiable equivalent to the product S1 times S3, and has the following invariant. So B1 of such an H, maybe H alpha beta will be the complete notation is 1. And one can prove also easily that the Kodaira dimension is 0. What is also interesting is that B2 is minimal possible, is 0. So this is historically a very important example. Now, the classification is done in the case B2 is 0. And this is why I pointed out this equality. Because, of course, take into account the definition B1 is imposed, is 1. The most natural strategy would be to look at B2, to try classification for minimal B2, for B2 is 0, and then to try to go on and to try to extend the methods to higher B2. So this would be the natural strategy, and this has been indeed followed. And we have here the first important result, which has been announced by Bogomolov in the 70s in 2 articles in Izvestia, considered by many experts to be incomplete. However, the result was correct. So the theorem of Bogomolov, I gave hopefully the first correct complete proof in my thesis, which appeared in International Journal of Mathematics, I think in '93, states the following: is X is in this class with B2 is 0. So I'll use only obvious notations. So this obviously means class 7 with B2 is 0. then X is biholomorphic. This means biholomorphic to either a Hopf surface or Hopf surface more general, in the more general sense than this one. And the general definition of a Hopf surface is the following. A surface H with universal cover biholomorphic to the puncture plane. This is the correct definition, the general definition of a Hopf surface. And they are classified. They are classified. Or to Inoue surface, which Inoue surfaces are surfaces denoted traditionally by S, and they are characterized by the following conditions. So it's a surface in this class with the following. So S is in this class with universal cover biholomorphic to the upper plane times H. The upper plane to time H. Oh, this is Caldeira dimension minus infinity, of course. Caldeira dimension. Yes, thank you. Minus infinity. Okay, maybe because it's the first lecture, I should here recall what this means. This means that id est, all the powers of the canonical line bundle have no sections at all. So this means that this is 0 for every n at least 1. Yeah, this is the condition. Now, why I give you this example? First of all, this should be maybe pointed out from the beginning that we understand completely these classes of surfaces, which means that we can also study moduli. So not only that in a set theoretical way are understood, but we also understand very well the families, so holomorphic deformations of such surfaces. So one can say the classification is completed up to biholomorphism. This is the conclusion. What is also interesting is that the result is easy. The result is simple. We have very few classes, which is, let's say, a similar situation compared to the algebraic, projectively algebraic situation. If you look in the algebraic situation to these classes, to these surfaces with a dimension minus infinity, you'll have that there are very few. This is classical algebraic geometry, which tells you which are the surfaces which are so rational and rule surfaces. So there are very few surfaces which have this property. So the idea is it's very difficult to make progress, but the result, the expected result, is simple. And now you see here why I say it's very difficult to make effective progress, because Bogomolov announced his result in the 70s, and it seems that the first complete proof has been given in 93. So the progress is very slow. And the point is that we have no possibility to reduce the problem to lower dimensional objects. And why? Because we don't have any existence, a priori existence theorems about existence of sub-objects of lower dimension, not only holomorphic curve. We don't know. This is the main problem. We don't know whether such a surface in this class allows holomorphic curves. And in fact, we do know, for instance, that Inoue surfaces don't. Hopf surfaces do always have curves. But Inoue surfaces don't. But we don't even know, for instance, if there is holomorphic foliation, even with singularities. In general, it is not known. Or even an entire curve, an unconstant entire curve. This is not known. Nothing is known in general. So we don't have any possibility to reduce the problem somehow to lower dimensional geometries, which means that all methods inspired by classical algebraic geometry will fail. Any lecture about classification of surfaces will start with a chapter, curves on surfaces. So if you don't have any curve, then we cannot start anything. This is, let's say, the main point. And indeed, here we have two important conjectures. I will come back to these conjectures later when I proceed with the proof for the existence theorems for curves. But just to point out from the beginning the role of the curves. So, of course, for higher B2, you are interested in the minimal case. So the problem is what happens, so let's say conjecture A. Conjecture A says that if you have a minimal class 7 surface with B2 strictly positive, so minimal, then X has B2 rational curves. Singularities are allowed. Singularities are allowed. So simple singularities that can occur. Can occur. Has B2 rational curves. And why is so important? Because by a result of Dlusky, Early-Klaus, and Thoma, I will come back to this result published in Tohoku several years ago. If this is true, so if true, why this conjecture is important? If true, it will follow that X is a Kato surface. So it's not the right moment now to explain what a Kato surface is, but this is a known surface in this class. So let me write it like this. Id est, it belongs to the class of known surfaces. And even classified in a certain sense. Known surfaces. So this is conjecture A. Now, how can I manage to use this? Yeah. Oh. Bon, alors. Non, je crois que je vais utiliser seulement un tableau. Non, je crois que c'est la meilleure chose. Et comment je fais pour le remonter? C'est pas grave. Now you see already the role of curves. The role of curves. Of course, it should be said, of course, that Kato surfaces do satisfy this property. So it's a reasonable conjecture. It's a reasonable conjecture. All the surfaces we know, which are minimal and have B2 positive, admit precisely B2 rational curves. Some of them might have also an elliptic curve, for instance, or two elliptic curves. Yeah, but all of them have B2 rational curves. As soon as we prove that, the conjecture is done. The classification is done. This is the idea. So we can complete the classification. And again, the result is easy. Here, there are recent results, for instance, of Early-Klaus and Thoma, dealing with families which moduli space of Kato surfaces. So we understand in detail the Kato surfaces, including moduli theory. So again, the result, if true, if the conjecture is true, the final result will be easy, as in the algebraic situation. However, it's very difficult to reach this point. Very well. We have a more modest conjecture, which, let's say, it will be, let's say, attacked, will be one of the goals of this series of lectures to show that for B2 is 2, the conjecture holds. And we have a program which is very advanced now to prove in general. So conjecture B, which states that if X is in this class, B2 positive, minimal, X has a cycle of rational curves. What means a cycle of rational curves? One of the following configurations. So this is a simple rational curve with a simple singularity. This is a cycle with two rational curves, and so on. So, and again, it is known that all Kato surfaces do fulfill this condition. More precisely, some, but in general not all, of these B2 curves form a cycle of rational curves. Why is this extremely important? So it's a weaker condition. Yeah? Because again, if we know conjecture A, that everything is Kato, and we know that all Kato do admit a cycle of rational curves. So it's a weaker condition. However, but by a much older result, this time of Nakamura, if true, let me like this, if true, by a result of Nakamura, it follows that X is a big deformation or degeneration, is a degeneration of blown up Hopf surfaces. Or if you want, of Kato surfaces, you know, which it's very interesting. You see, so this is true for Kato surfaces again. They do admit a cycle. Any Kato surface admits a cycle. So every known, let's put it like this: a Kato surface is a known class 7 surface in this class. Every such surface so is known to have a cycle. So it's a degeneration of blown up Hopf surfaces. So then we have this situation. We have a deformation in the sense of complex geometry. This means we have a proper submersion having a disk, a D, as basis, D in C here. And what happens, here we have the fiber XZ. And XZ is a blown up Hopf. One can even suppose that we have a blown up Hopf in B2. B2 is the second Betti number if B2 simple distinct points, pairwise distinct points. So XZ for every Z non-zero is a non-minimal Hopf surface XZ. So XZ is HZ blown up in some points X1, XB2, blown up like this. For Z non-zero. And in the fiber, so the central fiber, X0 will be minimal. So this means that these exceptional curves don't survive in the deformation. In fact, in the known cases, we know that the volume tends to infinity. They disappear. However, if the conjecture, for instance, the conjecture B is true, then always, yeah, even for every such deformation, in the central fiber, new curves in other homology classes will have to appear. So this is a consequence of the conjectures. Yeah? So it's true that the minimal in such a deformation, the exceptional curves must disappear because in the central fiber we have a minimal surface. However, if one of these conjectures hold, then we always get curves, also in the central fiber. But maybe, as I said, with other self-intersection numbers. What is the conclusion? The conclusion is that conjecture B, although, let's say, much more modest, is sufficient to classify surfaces in minimal, with B2 positive, up to deformation equivalence. So if true, we would know that all the minimal surfaces like that, with B2 positive, are in fact, all of them belong to the same deformation class. Namely, to the deformation class which generically contain non-minimal, so blown-up Hopf surfaces, and which also contains the Kato surfaces. So the conclusion would be that we have only one deformation class. And this would be very interesting and important for the topologists, because in particular, if conjecture B is true, then we have the same infinity, the smooth classification of the surfaces in this class. So if conjecture B is true, then every x in this class, 7 B2 positive minimal, implies X is diffeomorphic to S1 times S3, and the blown up in differential topology means connected sum with P2 with opposite orientation. To a power. Yeah? So let's put it like this. Let me write it like this. And here, from K is 1 to B2. So this means you make a connected sum between S1 times S3. So this is the differentiable type of a minimal Hopf surface. And you make connected sum with the projective plane with the opposite orientation. This is the differential topological interpretation of the blown up. So you see conjecture B solves complex geometrically the problem up to deformation equivalence, first of all, in particular up to smooth equivalence. So this means that the problem is, at least from the point of view of differential topology, is completely solved. It's completely solved. We only have one, for every B2, we have only one differentiable type. Okay, so these are the conjectures. What are the results I'm going to explain this week? So, theorem conjecture B holds is true. Conjecture B holds. So it's true for B2 at least 2. This is what is written. So the program is much more advanced than that, but it's not here the right moment to explain you technical progress, but only what is published and what is checked, and one can be easily explained and found in the literature. Fortunately, for B2 is 1, the two conjectures are equivalent, which means that for B2, let's say remark, for B2 is 1. So this implies also conjecture A, which means that we have completed the classification up to biholomorphism for B2 is 1. So let's say, which means that this progress We have Bogomolov theorem with a complete proof in 93, and now we have the complete classification, so which means complete classification. Complete classification for B2 is 1. However, it's very important to point out that the methods up to this point leads only to a cycle. And fortunately, I realized that this is the right, I have the right tools for proving this of a cycle, not more. So this is what I can generalize. This is what could be generalized, for instance, to the case B2 is 2. And we have here a program which should be announced as work in progress for proving conjecture B in general. Passing from conjecture B to conjecture I, we have several ideas, some of them in collaboration with George Druski here present, but for the moment we cannot announce progress, effective progress, general effective progress in this direction. So these are this is the context, the goals. And now something about the methods. I have something like 30 minutes left. This will be sufficient to make an introduction. On the gauge theoretical part of the tools, so the gauge theoretical tools I'm going to use. So let me put the ideas. The proof uses techniques and ideas from Donaldson theory. The role of the Donaldson theory was surprising for many people, And why? Because in the history of gauge theory, Donaldson theory was the first. So, as I will point out even today, the main ideas and the first spectacular result of Donaldson theory, but this has been achieved in the 80s, at the beginning of 80s, as I was a student. Donaldson theory appeared. Donaldson theory, so the part I need has been developed in 82, 83, as I said, as I was a student. And it's considered, let's say, the old gauge theory. And now we have Seiberg-Witten theory, and Gromov-Witten in symplectic geometry, which are much newer, of course. So these are so Seiberg-Witten theory. So let's say has been introduced in a mathematical way in 95. And Gromov-Witten has been developed in many stages, but I would say there's more or less it's contemporary with Seiberg-Witten, at least in a formal way, developed in a formal way, so has been achieved also in the 90s. And what is interesting is that in Seiberg-Witten theory and Gromov-Witten theory, we have theorems concerning curves, pseudomorphic curves. And we'll see probably some of my colleagues will, for instance, Francois, if he will give his series of lectures, part of it, of course, he will speak about the role of pseudomorphic curves. On the other hand, in Donaldson theory, nobody mentioned in the past connections between Donaldson theory and curves, and holomorphic or pseudomorphic curves. There was no mentioning about such a relation. And that's why I tried myself to attack the conjecture on class 7 surfaces with the most modern ones, with this one, with Seiberg-Witten and Gromov-Witten, and I failed. And now I have the impression, the deep impression that it's not possible and the Donaldson theory is more appropriate for our purposes. What is also interesting is that when Seiberg-Witten theory appeared, we had many conjectures, one of them formulated by Witten, stating that the two theories should be equivalent, or anyway, Seiberg-Witten should be stronger. And people begin in differential topology to prove any result, all the old results of Donaldson theory with a new method, and they succeeded. So in differential topology, everything that could be proved with Donaldson had been reproved afterwards with Seiberg-Witten in much easier way. However, it seems that for our purposes, we cannot find anything else but Donaldson theory. So this is, let's say, why I want to point out from a historical point of view. These are gauge theories, mathematical gauge theories. I don't speak at all about theories, about developments in physics and physical interpretations. What is the Donaldson theory we need? I gave to the organizers some notes, which of course I think are very useful. What I give here is a simplified version. I give much more, let's say, philosophical and historical details than in the published notes. In the notes will be probably have been distributed. I think it's better like that. On the other hand, I try here to simplify a bit. So you have there a formal and a complete, well-formalized version. Here I will simplify, but in a reasonable way, such that the ideas and, let's say, the techniques will be understood in detail. So, Donaldson theory. The way in which we'll need. So, Mg will be a closed, connected, oriented, four manifold with a Riemannian metric. Riemannian four manifold. When I say four manifold, I will always understand this. And smooth, yeah, so it's differentiable. Everything is differentiable. And EH will be a Hermitian two bundle. So you see Hermitian two bundle on M. So very concrete. I don't speak about general structure groups or Lie groups. I mean, I don't mention at all gauge theory in general, in principal bundles. No, I want to come directly to the point. And this D will be my notation for a determinant of E. Of course, which has an induced, so endowed with the induced metric. So it's a Hermitian, what is called a Hermitian line bundle. And I will fix a connection in this D. By this A, this is the space of Hermitian connections. So this is a convention which I will always respect, the space of Hermitian connections on D. This A, calligraphic A, means the space of connections, but which are compatible with a fixed structure on our bundle. There are many ways to understand connections. Fortunately, here, since I don't work with principal bundles, as I promised, but only with vector bundles, one can regard connections as defined by operators. So, you know, a connection can be identified with associated linear connection, which is an operator denoted sometimes with nabla. But anyway, you know the conditions. So this nabla must be C-linear, first of all, then must fulfill a Leibniz rule with respect to the function multiplications. And finally, because we speak about Hermitian connections, we have a compatibility. So again, a Leibniz multiplication rule for the compatibility with the metric. I'm not going to write all these axioms for you because I'm sure that all these notions are well understood. However, what is important here, and sometimes this is useful, that the same object, so connection, can be regarded as a horizontal distribution on the associated principal bundle, the so-called frame bundle. So in the first case, the frame bundle will be a U2 principal bundle. In this case, it will be a U1 principal bundle. It's the first interpretation. The differential geometers will prefer that. However, in analysis, people interpret the connections as operators, as I said. Anyway, so for us, the main object will be this. And this means what? We take all the connections in E. Again, this means Hermitian connections. The metric is taken into account with fixed that A is equal with A. This is precisely, not isomorphic or precise. So the induced connections on the determinant, you see, you can make in an obvious way operations with connections in the same way as you can do operations with bundles. Yeah, we can speak about tensor product of connections and so on. All the operations which are allowed with vector bundles can be extended to connections. So here what I mean, the induced connection on the determinant line bundle of E must be precisely E. Now, so this is a subspace in the whole space of connections in E. Maybe let me point out that this A of E, so the space of all Hermitian connections on E, is an affine space with a modal vector space the space of global forms on M with values U of E. U of E, this is the vector bundle of anti-Hermitian endomorphisms of E. So why? Because if you interpret the connections as operators and you make the difference between such operators, then you always get an operator of order 0. It's easy to say, to see, because the Leibniz rule in the definition of a linear conjunction fixes the principal symbol. And then if you make the difference, we'll get an operator of order 0, and you can prove that, take into account the Hermitianity condition, then it must come from a multiplication with a 1 form with values in this bundle. It's a real bundle. And our subspace is an affine space with modal vector space A1 of SU of E. So I want to be very accurate at this point because it's important to understand the objects we are working with from the beginning. So very well. Okay, so now we have a group which acts naturally on the space we are interested in. So I'll forget about the whole space of Hermitian connections. We are focused on this smaller subspace. So the gauge group is defined in the following way. I take the bundle of unitary automorphism. So in every point, the fiber in every point is just a two-dimensional Hermitian vector space. So you can speak about unitary automorphisms of such a vector space. And because it's the same, so the automorphism goes from the fiber EX in the fiber AX, you can speak about determinant, and determinant will be canonically a scalar. So you can impose the condition determinant is 1. Very interesting, although E itself is not an SU2 bundle. This is a very interesting remark. So acts naturally on EA of E in the following way. So let me fix F in G. F in G. F can be regarded as automorphisms like this. So here you have the bundle projection. So a gauge transformation is just a bundle automorphism like that, which is fiber-wise, as I said, unitary automorphism, and the determinant 1 in every point, in every fiber. And what you can do, you can look at the operator associated. So our operation, it's convenient to let the group act from the right. And interpreting connections as operators, the operation is very easy to understand. Namely, the covariant derivative associated to AF is just a conjugation, is F minus 1. So you take your linear connection regarded as operator of order 0. So let me write it like this, what I mean by a linear connection. So this is an operator, differential operator, operating like that. This is the space of 0, order 0 E-valued forms, or if you want sections, this is the same thing, sections in E. And this is just the space you take here, lambda 1 M tensor RE, and you get the space of E-valued 1 forms, E-valued 1 forms of E. So the derivative associated with A, such an operator satisfying, as I said, the Leibniz rule, so it must be C-linear, must satisfy a Leibniz rule with respect to functions, multiplications by functions, by complex values functions. And we also have a compatibility condition with respect to the Hermitian metric. So this identifying a connection with the corresponding covariant derivative, the corresponding operator, the action is given by this. This is the famous gauge symmetry acting on the space of connections. Of course, physicists have interpretations for all these objects. Connections are fields, weak fields, and so on, but we are not from weak interactions and so on, but we are not at all interested in these interpretations. What we are interested in is the condition of projectively ASD, anti-self-duality. So definition. ASD is, by definition, I take the connections in this bundle with the following condition. I consider the curvature, the trace-free part of the curvature, the self-dual part of this, and I impose that this vanishes. Let me explain you everything. The curvature of a connection. The curvature of a connection is an element, is a two-valued form. Is a two-valued form. So it's an element and A2 of U of E. Again, we see again this bundle of anti-Hermitian. So this notation, small u, suggests, so this recalls the notation from the Lie algebra. So Lie of UR. You see, so this small UR is the Lie algebra of the Lie group UR, the unitary group. And the idea is that what is done in classical theory of Lie groups using standard vector spaces can be constructed using an abstract Hermitian vector space, which can vary. So in this way, we come naturally to bundles. So here we have a bundle. So we have a family of vector spaces, which are Hermitian, all of them. And for each point, we look at the space of anti-Hermitian endomorphisms. And if you let the point vary, we'll get a bundle, a real vector bundle. And here we are speaking about two forms with values in this real vector bundle. So this is the curvature. The curvature can be interpreted like this. So the trace-free part of the curvature is an element here, of course, SUE, because we took the trace-free part of the curvature. And now comes this plus. What is this bar? This plus projection is an operator of order 0, defined in the following way. We have a bundle decomposition of this type, lambda 2 minus. This is a decomposition of bundles. So it's pointwise, holds pointwise decomposition. This is the bundle of two forms on M. So the bundle of two forms and on M, of M. So it's a bundle. So this notation is lambda, but should remind a wedge product. So it's, in fact, the second wedge product of the cotangent bundle, if you want. And what are these? We have, so these are the eigenbundles, or the eigen subbundles of the Hodge operator. The Hodge operator associated with G. So at this moment, in this plus, the Riemannian metric G on M is hidden, is used. This plus depends on G. It's very important. So star G, the Hodge star operator restricted to lambda 2, it's a symmetric isometric operator. So it's defined on lambda 2, And using this, one can see that the eigenvalues can be only 1 and minus 1. So this means that lambda plus minus are defined by the following condition. I take the star Hodge star operator and restrict it to lambda 2 plus minus is plus minus 1 times identity of lambda plus minus. So this means exactly what I said already, that we consider the subbundles, the eigen subbundles. Okay. Now, we can already, at this moment, we can already define the fundamental object of Donaldson theory. So as I said, it's easy to introduce the main objects. However, the difficulty is to see how these objects are used. So M ASD A of E, we take the space of projectively ASD connections on E, so satisfying this condition, factorized by the gauge group G. And this is, interestingly, this is, let's say, maybe one of the starting points of the Donaldson theory, this is a finite dimensional object in a sense which will be made precise immediately. So this is the Donaldson moduli space. What can be easily proved? One can regard this expression. So I take the curvature of A, the trace-free part. I make the square in the sense of the wedge product, and I take the trace. The trace, of course, refers to the endomorphism factors. Here we have elements in a tensor product, of course. And what is hidden here is the following operation. We have to think here, in every point, such an object, such the curvature, is a tensor product. It's an element in a tensor product. So when I say in every point, so the curve FA in a point X is an element in lambda 2 in the point X, tensor product SU of AX. The operation which is hidden here means the following. On the forms, I make wedge product, and on the endomorphism factors, I make product, matrix multiplication, and endomorphism composition, and take trace. Okay, and if I integrate this on M, I get a characteristic number. This is a consequence of Chern-Weil theory. Chern-Weil theory. Why? Because what we have here, the expression which is here, is an invariant polynomial in the curvature, invariant with respect to a joint action of the structure group. So this means that what you get must be a characteristic number, so a characteristic class evaluated on the fundamental cycle. And the result is the following, is 2 times 4C2 of E minus C1 square of E. This is called the determinant or discriminant of the bundle. E is a very important characteristic number for bundles of rank 2 on 4 manifolds. With P square here. With P square here. And on the other hand, using the decomposition, so decomposing of if A0 is if A0 plus if A0 minus, using this, one can prove easily that this is minus FA0 plus square L2 plus FA0 minus square L2. What is the corollary? Corollary is that if we do have ASD connections, so if this space is non-empty, or if you want the corresponding moduli space is non-empty, then necessarily you must have delta of A is non-negative. You see immediately what happens. So if this vanishes, then we get here, then the curvature reduces to the minus part, and this characteristic number must be a norm, an L2 norm squared. So must be positive, which is what is called the topological constraint. To the existence or for the existence of ASD connections, or projectively ASD conditions. I want to stop here because my introduction was longer about complex surfaces, so this means we are not late at all. So the introduction was longer, so I will need less time in the future for the complex geometric part, for studying the conjectures. So 1 hour is over. For tomorrow, I can explain you already what happens. Tant mieux. Tant mieux. J'étais bon. Très bien. Voilà, très bien. Je n'ai pas regardé attentivement. I didn't look carefully to the schedule. Très bien. So, now, the problems will be treated immediately will be the following. I already mentioned that this is a finite dimensional object. This somehow is surprising or very interesting because it's a quotient of two infinite dimensional spaces. So as soon as this space is non-empty, which is not always the case, because as I showed, we have a topological constraint, which is very, very important. We'll see that plays a very important role in the whole story, this topological constraint. So there are bundles which, for topological reasons, don't allow projectively ASD connections at all. This is extremely important. So I want to explain you this. And what I will give you is the Kuranishi deformation theory for instantons, for ASD connections, local models. I'm sure that many people here are familiar with deformation theory or with local models in complex geometry. For instance, how can one describe a germ of a moduli space of manifolds in a given manifold? This is a la Kodaira, in the sense of deformation theory of Kodaira. This is, let's say, probably the most popular, the most well-known example of local model, a theory of local models. We want to classify certain objects. We know that the answer will be a space, a moduli space. So the classes are parametrized by a continuous space. We cannot understand globally this space, but if we are given an object and we understand the geometry of this object very well, then we can describe a neighborhood of our moduli space in a neighborhood at this point. So this is the idea. And the same can be done for connections, for ASD connections. And then we'll see the finite dimensional character of the moduli space. And I also, because of this generous half of an hour, I can also give you a very important compactness theorem, which also plays a huge role in the whole story. So I'm very happy because with this I can almost complete the preparation, the gauge theoretical preparation with the main theorems which will be used in the future. And also which are also, meantime, main theorems of Donaldson theory. First of all, please note that we have here a copy of Z2, which is in fact, is plus minus identity of E, which is, of course, isomorphic to Z2, and it's a subgroup of G. And this acts trivially on the space of connections. So this acts trivially on A of E. Yeah. I can put here the point or not, doesn't matter. Now, definition, a connection A in the space of, let's say, all Hermitian connections doesn't have any importance here, is called irreducible. Irreducible. If, let's put it like this, one of the following equivalent conditions is satisfied. The first condition is that the stabilizer GA is minimal. The minimal subgroup about which we know that acts trivially is plus minus entity of A. So it's minimal, the minimal stabilizer. This is a way to put it like this. This is the favorite way in gauge theory, because in gauge theory you always use the symmetry of the given by the gauge group. But let's say the classical differential geometric point of view is about reducibility in the sense of parallel splitting of E. So E does not admit any A parallel splitting of the type E is L in the sum of two orthogonal line bundles. So you know what means A parallel. So if you have a connection, that you can use this connection to define parallel transport along curves in the base. Yeah, and then a splitting is parallel if it is invariant with respect to parallel transport defined by the connection. Parallel here, parallel. I can put it another way. So if saying that you have a parallel decomposition of E means in fact that the connection regarded as operator is a direct sum of connections defined on the two orthogonal subline bundles which are here. Parallel. So here it means orthogonal splitting. So E is the sum, is the direct sum. So E is, let's say, B direct sum plus C, where E is, voila, decomposes like this, and B is A of L, C is of A, and here is an orthogonal splitting. And we have, let's say, an analytical way of describing this. So we can look again at the covariant derivative defined by A, but not on the bundle itself, but on the bundle of trace-free anti-Hermitian endomorphisms. So ker of dA, but I take the induced connections on the bundle SU of E. You know, as I said already, you can make operations with connections. In particular, you can speak about the connection induced on an endomorphism bundle, yeah, endomorphism bundle. And SU of E is a subbundle there. So A1 of SU of E. So this kernel reduces to 0. This is a very interesting condition. Yeah? So it is very easy to see what is the relation between these conditions. For instance, you see if you have here a non-trivial element in this kernel, then this element will define real subline bundles in SU of E. And you look at the eigenspaces, in every fiber. Yeah, so these eigenspaces will be invariant with respect to the connection and with respect to parallel transport. And using this fact, you can see that the eigenspaces of an element in the kernel define you a decomposition of A, which will be A parallel. So I explained to you geometrically what is the relations between this analytical point of view, the kernel of a differential operator is zero or non-zero, and the reducibility of a connection. Very important. And then we have open parts, A. So A, let's say ESD A star, always the symbol star means subspaces of irreducible points. So which these points might here means connections, here classes of connections, gauge classes of connections. The condition, of course, the conditional irreducibility is invariant with respect to the action of gauge group. So now we have this very important subspace open, or this irreducibility conditions is an open condition. Yeah, this can be very easily seen using this analytical interpretation, and the fact that it's overdetermined elliptic operator. One can prove easily that the condition is open with respect to the same infinity topology on the space of connections. So we have here an open embedding like this. You see, the complement will be the space of reductions. So here we have A, E. So here is a complement, and A, E minus. So this is a space of reductions. Will play a very important role, the space of reductions. What will be very interesting to see tomorrow is that all these objects and sub-objects have complex geometric interpretations. Yeah, tomorrow we'll with holomorphic bundles, holomorphic vector bundles of rank 2, and splitting in direct sum of holomorphic bundles, and we'll have complex geometric interpretation for everything. Okay, so now, what about, let me formulate it like this. Theorem. Local models. Local models. Before stating this theorem, so the conclusion of the theorem, let me point out, introduce a very important elliptic complex associated to a connection. So let A be a projectively ASD connection. This ASD, this is very important. So let and CA, I define it like this. I take A0 of SU of E. So A0, again, this is my notation for global forms, order 0, degree 0 forms. A0 is just an alternative notation for gamma, for the space of sections. And then with dA, I go to A1 SU of E. And then I take dA again. You see here, you can, using the RAM type of formulae, we can extend the operator associated with A in the RAM using the RAM extension, the RAM type extension, to the space of forms of any degree with values in E or of every vector bundle associated with E. Yeah? Tensor powers, symmetric powers, endomorphisms, and so on. So in particular, you can continue and act with dA, with a natural extension of dA on the space of forms. And here I take this derivative, extended on one forms, composed with the projection on the plus summand of SUFE. So the associated elliptic complex. The fact that we have here an elliptic complex is a direct consequence of the ASD condition. Because if you make the composition, you just obtain precisely the multiplication with FA0 plus, which we know that vanishes. So the fact that A is in this space implies, obviously, so the fact that here we have a complex. The fact that this complex is elliptic, it's just follows from studying the symbols of all of these operators, and you see that this is true. Okay, so we have an associated elliptic complex. So if this is the case, we have the corresponding harmonic spaces, H0A, H1A, H2A, the corresponding harmonic spaces. Every theory of deformation of local models uses elliptic complexes and harmonic spaces. Note, please, that all these spaces are naturally GA spaces. GA is a stabilizer of A. GA is a stabilizer of A. So GA, so the stabilizer acts naturally, but usually in a non-trivial way. Then, so the index of this complex, so but defined like in the following way. So the first statement is the following. So it's H1 of CA minus H0 of CA minus H2 of CA is a topological invariant. This follows from Mathias-Singer theorem. It's, let's say, D of E, or DE. It's the expected dimension of the Donaldson moduli space, and is given by the following invariant, is 2 times D of E plus 3 times B1 of M minus B plus of M minus 1. Yeah, so this is B0 of M, if you want. So B plus, it's, you know, it's an invariant of the oriented form manifold. Then using the intersection form, you can decompose B2. You look at the intersection form, you regard it as a symmetric bilinear form on H2, no? The RAM, for instance, and you look at the signature of this bilinear form, the theory of quadratic forms over R, and you get a B plus and a B minus. Or if you want, use Hodge theory, and you'll see that the harmonic space H2 decomposes in naturally as direct sum of H2 plus. You take the harmonic forms, two forms which are self-dual, the harmonic two forms which are anti-self-dual, and you see that they give a orthogonal decomposition of the space H2 of harmonic forms. So, but important is the first interpretation, because the first interpretation shows you that you have topological invariance of the oriented four-manifold M. So, this is the first affirmation. Second, there exists a neighborhood, let's say UA of 0 in H1 of A, and a real analytic map kappa A defined on UA, which values in H2A. H2A, you see, it appears as abstraction space, as in complex geometry, which is GA invariant, Let's say, and the homeomorphism from what? So you take the zero space of Ka. So let me point out just in 2 words what this theorem tells you. You have here an open neighborhood of 0 in H1, A. So if you take the zero set of K, you can regard it as a system of scalar equations on a finite dimensional vector space, or anyway, in a neighborhood of 0 in a finite dimensional vector space. So we just have a system, a finite system of scalar real analytic equations. You take the zero set and the homeomorphism from what? You take zero set of this kappa A. This will be invariant because everything is equivariant with respect to GA. With values in M. So I said homeomorphism, yeah? So on the image. So from and a homeomorphism from this quotient on an open neighborhood of the gauge class A in the moduli space. In M. Of course, mapping the class of 0, yeah, so the orbit, so 0 is an orbit, yes, because G acts linearly on these vector spaces, so we leave invariant 0 on A. Maybe here I should also point out here 3 that GA is isomorphic to a closed subgroup of SU2. Yeah, in fact, one can prove that GA more precisely is isomorphic as a Lie group to one of the followings. So GA is plus minus E. In this case, acts trivially on everything. So the action is superfluous in this case. Here is isomorphic to S1 or SU2. These are the only possibilities. Yeah, these are the only possibilities in our case. And I will point out why. what are the possibilities? Now, what is the philosophy? The philosophy is very, I mean, the conclusion is very strong. The conclusion tells you that locally, a point in the moduli space can be obtained using elementary operations within classical finite-dimensional real analytic geometry. And what are these very classical operations? Imposing equations, quotient. But equations, finitely many, real analytic, and the quotient is by a compact Lie group. That's all. So locally, everything is finite-dimensional, but let's say elementary, one can say. Elementary in the sense that we just have a finite number. How many? You take here the dimension of H2, of course. And so, or you can, Ka can be regarded as a system, yeah, a finite system of real analytic equations. We impose these connections, these equations, we solve them. You obtain a real analytic space, which might be, of course, very singular. And you factorize this with, by the action of a compact Lie group, and you get a neighborhood of the moduli space. What is also interesting is that, let me point it here like this. Moreover, one has, so this key A of 0 is, of course, 0. This implicitly was already mentioned because I said that 0 is an element in the 0 locus. Yeah? But what is very interesting is that the differential in 0 of Ka is also 0. Is also 0. Always. So one can compute the first derivative of this K and prove that it's always 0. And very interesting, one can also compute explicitly the second derivative, but we don't need this. Why this is important? Corollary, if GA is minimal, is plus minus identity of E, that in this case I've told you that you have a Z2, but it acts trivially. You don't have, so this acts trivially on all vector spaces. Yeah. So minimal. What happens in this case? You don't have to factorize because the action will be superfluous. As I said, it's trivial. So you just have only a system of real analytic equations. So you have a real analytic space locally in the most, let's say, restrictive sense. Then let's say so M A S D A has a structure of real analytic space at A, whose tangent space, we can specify the tangent space, is tangent space at the orbit A of the moduli space is precisely H1. Why? Because the derivative of K vanishes. So the Zariski tangent space. So the Zariski tangent space of a real analytic space defined by a system of equations is by definition the kernel of the differential. This is the definition. The Zariski tangent space is H1A. If moreover H2 of A is 0, this is a very important case. Moreover, that not only that the stabilizer is minimal, but we also have that H2 vanishes. This is a very important, a problem to study. When H2 vanishes, then the same moduli space, so MA ASDA, is smooth, has a natural structure of real analytic manifold of dimension precisely D. Why precisely D? Because H0 in this case, H0 vanishes. H0 can be identified with the Lie algebra of the stabilizer. So if this is minimal, then it will vanish. So we know already that in the elliptic complex, we know by the equivalent definitions of irreducibility, you know already that for an irreducible connection, H0 vanishes. This is precisely our kernel, our old kernel. This is H0. So will vanish. So in our situation, if H2 also vanish, then the only contribution to this D of E, given by Atiyah-Zinger theorem, will come from H1. But it's the Zariski tangent space. So now let me finish the phrase and the lecture. If, moreover, H2 is 0, then is a real analytic smooth manifold of dimension D of E at A. This is why this topological invariant is called the expected dimension of the Donaldson moduli space. Now I have to stop for good, because now is the end. What is here the conclusion? The conclusion is that, you see, we understood very well, first of all, that the moduli space is a finite dimensional object, but can be complicated because you have to perform two operations, imposing the analytic equations and factorizing by a compact Lie group. If our connections is irreducible, so if the stabilizer is minimal, then one of the two complicated operations will disappear. So we just have a real analytic complex, real analytic space, but of course might be very singular, of course. However, if moreover we know that H2 is 0, then the two operations become trivial, because we have only the 0 equation with values in H2, and then the moduli space will be a related analytic smooth manifold of known dimension, and this known dimension is precisely the topological invariant of E. Yeah, so this is the ideal situation in Donaldson theory. So I'll continue tomorrow with compactness theorems and then with complex geometric interpretations. Thank you. Yes?
So what is the construction of the operator Ka?
The construction of Ka. I can give you the construction of K, but it's not easy. It's not easy. The construction is you have a typical construction of local Kuranishi models, and it's the same. It's a similar. Let me, just give you very roughly the ideas. So you have here, your connection A, and here this is the orbit. So this is G A times G. So this is the orbit. So first of all, you say this is A. This is AG. Then what can prove is that every connection which is close to A can be brought in what is called Coulomb gauge with respect to A. This means that any other connection is gauge equivalent to a connection in this space. You here take care for the adjoint from A1 SUE with values in A0 SUE. So this is the orthogonal complement of the tangent space of the orbit. Anyway, it's called the slice, the gauge slice. So this means that instead of factorizing by the whole gauge group, the whole space of connections, you look only in this slice. And in this slice, the whole gauge equivalence is, in fact, is defined by the GA operation. So GA will let invariant this slice. So this means that in a neighborhood of A, the G factorization, let me put it like this, around A is equivalent to GA equivalence factorization of this slice, SA, of SA. This is the first step. And then the second step, this is a very interesting trick. So, and then you say, okay, so I take the equation A, this equation, so F0 plus, and you take a weaker form. Here we compose this with, again, an adjoint, but this time an adjoint on the space of two forms with values in SU. And so this means that you can reduce, the local study of your moduli space to the following system. So you take connections of the form A plus alpha, where alpha is an element in the local moduli space, A1 of SUE, like this, satisfying DA star is alpha, star is 0. This is the slice condition. And dA star again of Fi plus Z0. And the point is that, you see what you did, it's very natural, it's very geometric. First you intersected with a slice, like this. In this slice, the tangent space of the slice here is precisely the L2 orthogonal complement of the tangent space of the orbit. So it's very geometric, the idea. So first of all, you reduce your gauge factorization, which is infinite dimensional, to a factorization by GA. And you do that looking at what happens in a slice. And then you take a weaker form of your equation, you see? So instead of imposing brutally your ASD condition, you compose it with an operator which comes back in A1. And what we can prove is that this is a smooth manifold using implicit function theorem. This is a smooth submanifold of the space of connections, not necessarily ASD, because here you weakened the equations, having precisely H1A as tangent space. This is very easy to prove that, because here you compute the derivative, and you see that if you take this derivative, if map with as regarded as a map with values in a suitable space, then will be a submersive. This system is submersive. This is the idea. It's a submersion. If this is a submersion, it defines a smooth submanifold. You see, okay, so now what you have a smooth submanifold which has a good tangent space, H1A, so it can be identified with H1 if you want, but it's not quite a model of the moduli space you wanted, because you weakened the equation. However, you can prove that on this smooth submanifold, imposing, you have to come back to the brutal condition, Fi plus equals 0, but you can prove that on this submanifold, the equation Fa plus, so on this submanifold, so this is really the proof. The equation Fa0 plus is 0 is equivalent to the same thing projected on H2. You see? So what you did, first you replaced the G factorization with a GA factorization of a slice, number one. Number two, you weakened the equation and you got a smooth submanifold having H1 F tangent space. And then you have to come back to the original equation. But you can see that on this finite dimensional submanifold, the original equation is equivalent to its projection on H2. And the projection on H2 gives you this kappa A. So this kappa A is obtained in two ways. You restrict your equation, initial equations, FA0 plus on this submanifold. You compose it with the projection on H2, and also you identify this submanifold with its tangent space. And you get precisely HA, yeah, between the spaces you want. This is precisely the proof. You can find this proof, for instance, in my book with Martin Lübke about the Kobayashi correspondence. You can find this proof in detail.
Other question? So it's not tomorrow morning at 8:30.